It is a pleasure and an honor to be in front of you again, and it's a topic that is very near and dear to my heart as far as modeling is concerned. And over my career, I've always talked about this, and you're going to get the essence of it in a short 50 minutes or so. I'm just going to jump into the electronics cooling, thermal management, and approaches and principles as far as the modeling is concerned. And it is a very, very, as I mentioned, important topic to me, as has been integral part of my career over the years. If I were to define modeling, it is defined as the process of obtaining a relationship between the independent and independent parameters, such as in the case of electronics, cooling, junction temperature, or heat sink case to ambient thermal resistance as a function of velocity, board conductivity, name it, depending upon what your independent parameter is that you can control in the process. So the objective is to come up with an equation, as you can see here, where we can, by varying, for instance, the velocity, in this case, the resistance as a function of thermal resistance, as a function of the velocity, air velocity, you can see a point of return and get into asymptotic condition as the velocity increases. This is a model. This is a very simple model that allows me to do a lot of parametric analysis. I can look at the velocity from 1 meter per second all the way up to 5 meters per second and see what my performance is going to be as a result of it. I can make a decision. If this resistance is acceptable, I can go in there and design a cooling solution, whether it's air or liquid or what have you, depending upon the process. So as an engineer, the ability to be able to model, which we apply the laws of physics, and I underscore the point of laws of physics to a given problem. And in our case, are the thermodynamic laws that we use in order to be able to go through the modeling process. So why modeling is so important? Here is an example of the electronics that we deal with. You all come from different industries, and some from consumers, some from biomedical, some from aerospace, automotive, just name it, and some from whatever you call this. I think this is a Bitcoin mining, and it's a nightmare of both electronics packaging and also cooling. As you can see, the fans are placed on top of the heat sink. And it becomes a very challenging process for us to be able to solve this and come up with the appropriate cooling solution. And why modeling is so important is because design analysis and optimization, we don't want to have a system like this, what you see in here. We want to have a system that is potentially optimized, or this one is potentially optimized. And when we have applications like the aerospace applications, we have really a point of no return. I cannot send somebody up there to repair the electronics. The electronics has to be robust. Equally as important is the issue of cost. Irrespective of what industry you work at, the cost is a huge parameter that we have to be able to focus on and be able to solve the problem accordingly. And equally as important, because of the fact it's a very, very competitive market. The whole world is competing in our space. It is important to produce a product that's right the first time, and we don't introduce something that is got a thermal problem or electrical problem and has to come back to us. The modeling would enable us to do these three tasks and hopefully reduce the design process. So what are the fundamentals behind modeling? There are effectively three approaches, three broad spectrum approaches. Integral models or first order solutions. Some people call it the back of the envelope. It's demeaning to call integral modeling back of the envelope, but the intent that the messages conveys is it enables us to very quickly, by hand calculation, or go to some of these software tools like Excel, MathCAD, MATLAB, just name it, Mathematica. There are a ton of tools on the market that you can convert these models into a very, very effective solution procedure. So it enables you to vary the parameters that's important to you in order to be able to solve it. So the integral model is based on integral form of the conservation laws equation, control volume, yields endpoints of dependent variables, applicable to any problem domain, and can be developed with moderate amount of effort. This is what we've effectively learned when we go to our undergraduate training, and we learn the basic principles, and we should be able to put it together when we start applying these to different problems. Then there are computational methods or second order solutions that's based on the differential form of the conservation laws. And it provides us with a distributional profile of the dependent variables when we go through the process, and can be applied to problems that are phenomenologically understood. What do I mean by this lofty word? We have these beautiful tools on the market that have gone through numerous validation and so forth, but they have a very, very defined capability as far as mathematics that apply to the problem. When I look at it, for instance, flow through a heat sink, that the top is covered like this, and it's a ducted flow. It's a very, very defined problem. And the models would work very effectively, even for some of the problems that are open channel. A lot of work has been done on the heatsink, for instance, that we can address the open channel, like the picture that you see in the bottom. But we have to remember that the mathematical models that are deployed in the computational tools, they're very defined, and we need to make sure that it is applicable to the problem that we solve. When we talk about experimental, the last level of modeling, which is I call it the final solution, it's typically applied to the problems that are not phenomenologically understood. Take a look at this problem that the flow is coming through the heat sink, and it is departing very rapidly to the front, and the flow is actually going around and coming back in. And this higher pressure region, and also with the development of the boundary layer within the fin field, is pushing this smoke or flow visualization out of the heat sink. It's a very, very complex problem domain, because you see the variety of flow regimes into the same control volume. If I put a control volume around this heat sink and try to analyze it, you can see how complex it is. In the one control volume, you have everything that's happening. So when we do the experimentation, it's typically gravitated towards the parts that we cannot really verify, or we use the experimentation for validation of a problem that we've done, either with integral model or with numerical simulation. So the fundamentals behind the modeling procedures that we have are the conservation laws, conservation of mass, momentum, energy, and the equation of the state. You probably all remember what these equations are as far as application is concerned, but the equation of the state is like the ideal gas law. When we have variation of the fluid properties with temperature or pressure, we need to deploy the equation of the state to make sure that we capture in the effects appropriately and correctly. But all of these apply to the modeling, from integral, computational, as well as experimental. Some of you may wonder, what do you mean by applying conservation of energy and momentum and so forth to experimentation? My statement and philosophy has always been a good experimental is an excellent analyst. If you don't analyze the problem up front, doing an experimentation is a lost opportunity and prone to a lot of mistakes in general. So the laws of modeling, conservation laws, and equation of state apply to all three phases of the modeling that we discussed here. And just for the sake of, I know it's afternoon or morning for some of you, just to remind you that you've seen these equations before as far as the integral model is concerned, of the conservation laws and the numerical version of it. When you look at, for instance, this equation, that's Navier-Stokes equation, it is a very complex. There's only one or two closed form solutions, or a handful of closed form solutions to it. The rest of it has to be solved numerically, and inherently it is unstable. Now we add numerical to it, numerical calculations or solution to it, the chances of making a mistake and so forth is significantly larger as a result of it. But the equations that we use that results in either endpoints in the integral model or distribution of the independent parameters are these. In the background, in your CFD tools, you're solving these, and hopefully when you get better with the, or if you're versed in modeling, analytically, you're using these equations on a regular basis. So when we talk about the options in analytical modeling, to get a better sense of the levels that we have that we can progress to go forward, let's take a look at the component that resides on a board. It's a highly 3D flow, meaning the heat goes in this direction, the heat goes in this direction. When it gets to the board, the heat is dispersed here, it's lost through here, and is lost through the background. So oftentimes we come up with this very, very simple expression. We reduce this sort of a triangular resistor that has even more components to it to a single resistor. I don't know how to do this, but somehow people do this on a regular basis, and you can see how a complex problem is simplified to a very simple equation. There is a reason for this, and I'm going to mention it a little bit later, but we try to one-dimensionalize the problem as much as possible in order to be able to solve it and solve it quickly. So these resistors that are penetrated into the calculation domain, they're all over the place, and they should be used with a lot of caution. So resistance model or resistance network is certainly one approach. And we can put all these resistors together in a 1D and effectively come up with the junction temperature expression, which is the most important parameter that we have to deal with in electronics cooling as a function of everything that resides in the path of the heat flow in the system. And we have to account for junction case resistance. We have to account for a very important parameter called the spreading resistance, where the heat comes here and gets spread, or when the heat comes here, it gets spread. And we have to be able to account for that in our modeling. But again, 1D assumptions simplifies the problem. Certainly is a good point of reference, but not the absolute solution. Is a good point of reference for us to pick up the problem and see where we are and what we have to do in order to solve it and solve it effectively. The area that I sort of lean into and I like very much is called the integral modeling. When we use a series of control volumes at different locations, and in this particular example, for instance, we put one control volume around the component. I can even miniaturize that further and go right around the device if I have to. Then we put another control volume around the fluid, one control volume where the heat comes to the leads or the balls and then gets into the board, and then another control volume on the board. So if I merge these control volumes and apply the first law of thermodynamics on the conservation of energy, I have this model. And then the model that I have is significantly more comprehensive. Based on the resistance network that we had, we're going to get a model like this. Based on the integral model, look what I have. It's something that's significantly more comprehensive. Remember what the objective of the modeling was the ability for me to change the parameters so I can come up with the variations as to where my solution resides. In the case of, remember, I showed you the resistance as a function of velocity. I had the ability to select different velocities and go to different locations and see what my junction temperature was or my thermal resistance was as a result. So this enables me to look at the temperature of the board, for instance, look at the heat transfer, look at the heat transfer from the leads of the device, look at the R effective for the device. I can look at the effect of the adjacent boards, as you can see here, and look at what happens in the adjacent as far as the fluid is concerned. So it gives me a lot of parameters to vary. So you can see the resistance model, a simple one-dimensional integral model, and the differential form of it. It gives you a very, very broad spectrum solution as far as temperature variation, pressure variation, velocity variation in the field. So you have these three options of modeling that you can deploy when you go through the electronics cooling problem or any problem. Let me just sidestep for a second and talk about the thermal resistance. That's a parameter that's coming to the our calculations, and it's a gift or a curse from our predecessors before modern electronics that came into the picture when we had power devices or vacuum tubes that would reside on a board, and bulk of the heat would be coming from the top, and was very little connection between the component and the board. Whereas in modern electronics, we have a significant connection, and something like 60–70% of the heat is conducted to the board versus going through the top. So whether it's psi, theta, rj, whatever you want to call this, the net result of it is the sum delta t, sum delta t divided by power. So obviously the power is ambiguous. The delta t is ambiguous depending on where you measure, and it is a good tool as a point of reference to use, but it should be used as a point of reference, not as a design tool. And there have been some good efforts been put in place by folks in Europe to come up with a compact model, and some of the activities in the US. And they've tried to resolve these by coming up with a better definition of the package resistance to board temperature, ambient, and so forth. But we found the use of these compact models more so in numerical computation or the CFD models versus the analytical models that we use. So as a quick example or something that you ought to do when you have a few minutes that you want to play with the integral model is imagine that you're standing in the middle of the room and you're dissipating so many watts, about typically 100 watts, and you know the ambient temperature, you know the reference temperature, and put a control volume around yourself and see whether you can come up with the surface temperature of your body, where you have conduction, you have convection, heat transfer, and you have radiation. And for the sake of quick calculations, not that you should ignore it, but in order to linearize the problem and get rid of the nonlinearity on power to the 4, see whether you can calculate the surface temperature as a function of parameters that are around you, meaning ambient temperature as a function of the conductivity of your body to the board, to the floor. And you'd find when you go through this calculation, and this is the integral model of the conservation of energy, all the heat that's coming in, which is in this case is 0, there's no heat coming in, that's generated is about 100 watts. And what's going out is by convection and conduction. And we make an assumption the problem is steady state, so there's no accumulation. This is the dt divided by the time. So we assume that this is steady state. You've been sitting in the room for past 45 minutes. So it becomes a very simple linear equation for you to solve. 100 watts equal to the summation of these, and you can come up with a very accurate, reasonably accurate surface temperature of your body. And you're making an assumption as the drawing shows that you're 2D. You don't have any mass that's going to store energy. Well, ironically, what a component sees on the board, which our objective in the electronics cooling is to make sure what the junction temperature is for the worst possible ambient. And ambient typically is 55, or in some cases 70 degrees, in some cases 25 degrees, 35 degrees, depending upon the given workspace that you work with, the consumer electronics, biomedical, what have you. And the question is, can I cool this board with 1 meter per second, 200 feet per minute, when the air temperature is 45 degrees C? So I have air coming in at 1 meter per second, and it is at 45 degrees C. And I want to see what should I do with the cooling? What's the junction temperature? So please keep that in mind, and also please keep this in mind, where we are going to apply these equations in order to be able to come up with the junction temperature of this device that you see here, and see what is our cooling solution. So you can get a sense of what the level of the thermal modeling is. So we put our control volumes at different locations, as I mentioned before. We apply conservation of energy to every single control volume. And remember, these are linked to each other like the resistors. And if we do the resistance network properly, it is the same thing as the integral model. But oftentimes, because of the fact that we don't know where the heat is going, it becomes very convoluted with that triangular resistor that I showed you. So the control volume gets that ambiguity out of the way. So when I put that equation together, the whole thing, I come up with a very nice equation for junction temperature. Which is this is the parameter of the component. This is the power. We have the case temperature effect, and this represents the heat sink that we may have to use. We have radiation component in here. We also have the conduction going through the system, and the board is also a parameter here. And in order to calculate the approach air temperature, we know the inlet temperature is 45. But the approach air temperature to the device, I'm talking about making reference. If I stand here, if I put a thermocouple here, what is this temperature? And we call this the approach air temperature, or T sub A, to the device. So I can calculate the approach air temperature. I have the T sub A. I should be able to calculate the temperature rise or the absolute temperature as a function of all of these parameters that's in here. And remember, based on the conversations that we've had before, if I'm dealing with the silicon-based type of devices, typically the default in the market says 125 degrees C for the worst possible ambient. As a design rule, we want to be able to about 10 or 15% below that level, because there are so many ambiguities in electronics packaging that we cannot put our arms around it. So we want to give ourselves a little bit of a margin, and then we leave the 110 to make sure that we have about 10 or 15 degrees variation there. So we come up with this ATA factor that you've heard me talk about it before in other presentations, that says the TJ calculated, junction temperature calculated, minus the reference temperature, that's why I put the infinity sign in here, divided by the spec, whatever the manufacturer of the device says, minus the same ambient, should be less than or equal to 90%, or that 10% margin that we were talking about. So as a rule at ATS, for instance, when we go through the design, if I don't have that kind of a margin, we don't call the problem closed. We have to have the margin in there. That's just a good engineering practice. Whether we design a cooling solution, we designing automotive, space vehicles, doesn't make any difference. There is nothing absolute, and if you're at a 95%, there has to be a very, very, very hard discussion and justification whether that's acceptable or not. The 10% safety margin has always been our target, and I think it's a very, very good practice for you guys when you work in the field. So remember that we talked about the parametric modeling. We have this model, T sub j, as a function of all of these parameters, and we're going to go and change the things that we can change. For instance, I can change the speed or effective heat transfer coefficient of the heat sink, and see what the impact of it is as a function of velocity. So that's what we're going to go through. So we want to see what's the calculation that we have to do. Are we going to meet the 90% factor? So at first and foremost, if I don't have to use a fan in my system in an air-cooled application, I am king. Everybody loves me as a result of it. So we go with natural convection. We see that the ATA is 1.9, a factor of 2 higher than our target. Okay, I go to 3 meters per second, and I see the result is 1.3. I go to 6 meters per second. I see, okay, I'm getting to my target of 0.9. It says that I have to have a high velocity flow in order to solve this problem. And I take it one step further. I say, what if I go to 9 meters per second? And I see I'm getting to asymptotic conditions. Remember that curve that I had drawn for you before? We get into the point that, I don't know why it's doing that, but we get into the point that as I increase the velocity, I have a diminishing return, and it doesn't pay off to increase that. Just remember, as a kind of a quick side note, the power that's consumed by the fans in the electronics is one of the largest power sinks that we have, and less fans you use, less power you consume, less noisy it is, and it's going to work properly. Okay, the next step is, what if I have an indication here that I have to use is, in order for me to cool this, I have to use a high-speed flow. And then it says, what if I want to increase my board conductivity? And I see that there's no change. That means that the device, I've gone from a 4-layer to 8-layer board, and of copper layer, and I see that it didn't have much of an impact. So it suggests to me that the board is not the component is not heavily coupled to the board, and I can't use the board as a heat sink. So the next thing is, okay, let me just play with the heat sink. I get a more efficient heat sink at 3 meters per second in here, and I put a heat sink of this value of heat transfer coefficient. It puts me at 1.9. If I want to stay at 3 meters per second, which is a very nominal velocity that I can work with, and especially in modern electronics, it seems that I'm at the level that I can call this design a good design, but I need a very efficient heat sink in order to be able to achieve this level of work. So you can see, before I go run into an experiment, before I do 15 CFD simulations and so forth, with some very quick analytical modeling, utilizing an equation like this that you ought to develop on your own. It's very simple, 4 equations that we showed you. These are the 4 equations that you have to remember and memorize. These are the 4 equations. You don't need anything other than these for most air cooling applications that we come across. With those, very quickly, on an Excel spreadsheet or any of those software tools that I mentioned, you can come and hone down on the problem and say, okay, I need a heat sink that's going to have a resistance of case to ambient of, say, 0.4 degrees C per watt at 3 meters per second. I have a very, very good possible solution. Now I can go into the next phase. Now I need to verify it. And local model said that now my solution is confined. I don't have to go and fetch around and look around and start playing around with different things and not getting anywhere. Very organizedly, I can see where I need to focus on and come up with a solution. Remember, one of the objectives is to reduce costs and be able to come to the market first, which is very, very important. So you can still get the appreciation of, with a very simple example of going back and forth on the different parameters, how we can close the solution and look at the junction temperature, which is the most important parameter in electronics cooling, and see whether we can meet the requirement. So when it comes to the simulation now, we have two options, integral and numerical. Integral modeling delivers a point, and numerical modeling delivers a distribution for the nth time. We can do it at the component, PCB, and system level. And then remember, the difference between these two has to be within maximum of 20%. So I've done my integral modeling. Now I pull off my CFD tools, and based on this, based on the values that I have, I've defined the boundary condition now. It's at 3 meters per second. Maybe I can change it to a little bit higher and lower. And once I finish with my numerical simulation, I must be within maximum of 20%. Our point of comfort is around 10 to 15% typically. But just to be on that 20% bandwidth, then I have a solution that I have high degree of confidence that's accurate and it goes through it. So let's go through an example of what happens in the design process or modeling process. So we are at the earliest stage of design, T-junction, model development, CFD analysis, comparison of the results, and junction temperature calculation for a typical ATCA chassis or whatever the models look like these days. Questions are concerned, are there techniques to provide fast results within engineering accuracy? Can we reduce the design to solution time? Catastrophic results if we wait until the PCB layout and component placement are complete. This is when I call it catastrophic, is because of the fact, if I go through the stage, I have incurred significant costs. We want to be able to do this at the concept stage, that our electrical engineers and system designers have come up with a system, they've laid it out, and they think the board is going to look like this, the system is going to look like this. We want to go through an analysis and have a thermal input to the team versus waiting for the parts to come back. By this time, we've lost time and we've spent tremendous amount of money, both soft money and hard money, engineering time and outsourcing for production purposes. Solution approach will lay the ground for a successful design and improve your success by doing thermal design right the first time. So typically, analytical modeling takes 2 hours or more. It's a very complex problem. You spend maybe 2 or 3 days, and you have to analyze a lot of little details. But if it's a simple heatsink design or component on the board, it should be a couple of hours to maybe 4 hours. CFD modeling and CAD takes about 4 days, and experimentation takes about 3 weeks to complete, because you want to have the experiment that's close to reality, not something that's going to be fictitious. Because you know what the biggest problem is? When you do an experiment, look at your past experiences. If somebody comes and tells you and shows you some data and said, I've measured it, intuitively, inherently, you accept it without questioning. But if I tell you I analyzed this, you're going to put 15,000 questions in your head and your colleague's head of how do you know your assumptions are correct? How do you know this? People believe data. So if I don't collect data accurately and based on laws of physics, based on a real problem, I don't have a solution. I have a very dangerous solution that I can provide to the field and create a lot of havoc. So earlier stages of design, cooling chassis can be significantly challenged, and means your product success could result in success or failure. CFD model should be run after the analysis to verify the analytical model and the fine-tuning of the solution. Mock-up models are recommended for experimental verification when the problem is complex. Can we develop a single equation that can readily provide the designer with an approximate device junction temperature. And what we're shooting for is something like this, that we have all these parameters that impact it, and we can come up with the junction temperature of the critical devices that sits in the system. So we set up a model of the ATCA with the dummy boards. You can see the thermocouples coming out of the system. Is fan trays on either side, and it's a commercial ATCA package. And the sensors that you see, we have hot wire anemometers that we have put in place in order to be able to measure the air velocity and air temperature when the flow is coming from right to left. And the fans are powered by a 48 volt DC. And you can see the placement of the candlestick sensors at different locations, and you can see the dummy loads that we put in place in order to be able to measure and account for the heat load. And the velocity sensors that you see here are the ones that are giving us the velocity distribution and the temperature, air temperature distribution. And the sensors are a very small form factor, as you can see here. I don't mean to put a commercial in place, but there's a beauty of these sensors that, number one sensor measures both velocity and temperature at the exact same location at the same time. And the form factor is so small that it doesn't disturb the flow and the results of your calculation. So we go through the standard system analysis. We have a fan tray. We have the system curve that are shown here. And the point of intersection is the one that gives us the flow. And we want to be at a region that is stable. We don't want to be somewhere around here, which is highly unstable as far as the fan selection and so forth is concerned. Then we calculate the total resistances. And then these individual resistances associated with in developing analytical model, the fan, the filter, the honeycomb, and so forth, that's in the process. And we have to account for every single one of these because we need to put this total resistance together in order to be able to calculate the system curve. And once we have that, we want to calculate the volumetric flow rate that's in front of the system and compare our measurement versus the analytical modeling. When you have effectively a channel, we can calculate the effective volumetric flow rate through those channels based on the opening and the board layout. And we can know what the velocity is based on the system curve that we got. And on the heat sink, we obviously have these equations that we've seen before, that where we can calculate the case to ambient thermal resistance of the heat sink as a function of velocity, so we can see where we need to be in order to be able to cool with this kind of a heat sink at what velocity in order to be able to cool this device down. So we have all of our analytical tools in line, and when we put the whole thing together, and we rely upon some of the junction temperature resistances in order to be able to bound the flow, and we can see that the equation that we get for junction temperature or junction temperature rise is something that embraces all of these parameters. Now I can change it in order to make sure that's giving me the data. The reason we are using these resistors is because of the fact time is of the essence, and we want to ballpark it, and we put a variation on the values in order to make sure that if there are any kind of a ambiguity in the measurement and reporting of the RJ values, RJC, case to ambient, junction to board, etc., we can account for it with parametric analysis. But the good news is we can come up with a very compact model to give us the junction temperature as a function of all these parameters and be able to see whether it's going to survive at the level that we want. So we put these values in here. The overall power dissipation is about 300 watts in one board. We're going to vary the air velocity from 0.5 to 2.5 meters per second. We make an assumption that the outside ambient for the worst possible case, typical of the telecom and so forth, is about 55 degrees C. And now we go through the whole process. And also, designer wants to vary the component heat dissipation between 30 to 55. As we all know, the components are never at the power that they think they are. And when we go through the design, by the way, as a normal practice, is to make sure that we design for the worst possible power dissipation. The question we typically ask a designer is, can the system see maximum power dissipation? If the answer is yes, our cooling solution must address that. If the designer assures us that we're going to be at a nominal, say 40 watts, that's what we decide when we design the system. But the question is upon you as a thermal engineer or a system engineer to ask that question, can the system see the maximum power? What if I have 100% traffic at one point on this system? Can the device shoot up to 55 watts? And if it does, the system has to survive. We've had examples in the past. You may remember in Super Bowls and so forth, when they show a commercial, everybody goes and logs into a site, and the systems crash due to the traffic, and oftentimes it's due to a thermal problem because of the fact the system is at a most elevated power demand and it cannot cool itself off, so it shuts down. So we solved the equation for T sub j. We know the maximum allowed temperature is given to us, and now we have an equation here that we can vary the power, we can vary the air velocity, and see where it lands as far as the junction temperature is concerned. As I mentioned, this could be junction temperature or junction temperature rise. We are engineers; we can set it up at the level that we want. And we also have developed another useful equation to find the required heat sink thermal resistance as a function of other parameters. So not only we can see what the junction temperature is, if the velocity has to be high, I have to deploy a heat sink in order to reduce the velocity because I don't want to pay for the stuff that we talked about before. So with this equation, I can very readily calculate the heat sink resistance requirement and be able to select it from the system. Now let's go to CFD. So we did an integral model. We set up the experiment. We're going to do the CFD just to show you all the three phases. And you can see the modeling that's taken place here. You saw the examples of the board. And we don't sit down and model those intricate components. That's just an utter waste of time and doesn't get you anything at this level of analysis. We put this block of heaters, as you can see, with the appropriate height to simulate the flow. But the flow around the component at this level is not necessary. And we get rid of everything else that's going to complicate a computational model, because the intent is to see what the temperature rise is, what the approach air temperature is, and whether we can have an appropriate heat sink for this device. So some of the boundary conditions for CFD: specify fan characteristic curve, specify air temperature at the input, specify static pressure as 0 at the outlet, add extra length of the virtual duct to the outlet to prevent numerical error. A lot of people put their computation cell right on the package, and they don't realize that if you're using a fan or other fluid movers, there's a flow associated with that, and you have to walk away from the system in order to allow for the fan model to work effectively. Specify the heat loads on all components, and don't worry about modeling all the filter details and so forth and perforated plates. There are very much resistance models available for those. That's going to reduce your computation time. Otherwise, you're going to wait for days for the solution to converge. So when we compare the experimental velocity values that we have, the average velocity in linear feet per minute, we have the thermal board, we have the full heat, and the fans that are 48 volt DC, and you can see the variations in the boards that are existing here as far as the velocity is concerned. One thing that we did here, we turned the fan on the numerical simulation. We turned the boards on and off to see what the impact of the change of density is, and we can see here that it does play a game. As the density increases, as the air temperature rises, the air density increases, hence lower pressure and consequently higher volumetric flow rate. And we see this very much in here. So our simulation is following the logic of what we expect to see from the physics standpoint. And now we're going to put all three together and make a comparison. Remember, our objective is 10 to 20%, 20% being worse. So here is the experimental data. Here is the computational data. Here's the analytical data. And we can see that this is within 10% just about. This is more like 25% or so. And but this and this are much closer as we expect. This is again within 20%. What it tells me is I have a good model. Experimentation verified my numerical simulation. My analytical model puts me in the ballpark, but obviously it's not as close as I'd like it to be. I expect to see the experimentation analytical model to be close, but I'd like to see this closer, more in the neighborhood of 15%. So if I had any doubts, if I didn't have the numerical simulation, I would go back and recheck my analytical model, and I would recheck my experimentation, make sure that I have no errors in here. But you can see now with this, I have a high degree of confidence that the results that we generated is very accurate with the information that's given to us, because independently I have verified the solution. And notice one thing that we did not do. We did not do the measurements here and then take that information, put it into our CFD model, and then so now we know exactly what the inlet velocity is, and then simulation and CFD comes in within like 2 or 3% of each other. That's a no-no. The solutions have to be independent. That means I do the say analytical modeling, you do the experimentation independent of me. We come together to the table. Maximum we have to be within 20%, and we are almost there in here. But the computation and the experimentation are much closer. So you can see the benefit of it. Now I can walk into my design team and say, I have high degree of confidence based on the information and the boundary condition you've given me, the power, the temperature, etc., etc. I have a solution that's going to work. Our junction temperature is going to be X. We need a heat sink of certain performance. Our fans have to be Y with certain voltage and volumetric flow rate in order to meet our requirements. So the basics of the design is done. Now the rest of it is for the mechanical packaging team or the circuit engineers to go and put this information together and make sure they deliver for you what has to happen. So when we look at this, and if you really had a good feeling and understanding of what I showed here and how these modeling is going to help us to close the solution and give us the design information that we need. So irrespective of the market sector that we work in, we have a variety of different applications that we are working through it. Notice none of these modeling had anything to do with the market, with the market sector or the deployment site. All we need to do is know is the boundary condition. Where is our system being deployed? So we have to envelope our design by running different what-if scenarios to make sure that we're addressing that. Early stage analytical modeling enables you to ascertain the critical areas and examine possible solutions. So right here from the analytical model that you're putting your Excel spreadsheet or your whatever model that you have, you can go in there and change these parameters and develop a variety of design curves for junction temperature as a function of velocity, junction temperature rise as a function of board conductivity, as a function of neighboring boards power. Just name it. It is so powerful to be able to go in there and say, okay, I can change these, and as long as you have a model and really envelope your design, and to the point of, hey, look, to your circuit designers, this board and this component with the power dissipations you've given me, you cannot put another board of the same power next to it. You got to locate that in a different location of the system, because the coupling that takes place between the two could adversely impact the thermal performance and the performance of the system. Design jeopardy can be identified in short few minutes by use of the analytical models, as I just explained. Higher order solutions such as CFD and experimentation performed after analytical modeling will enable you to verify design and fine-tune results. Save time. Analytical tools are much faster than CFD experimentation and are ideal for first-order design iterations. In the past, when I've talked about these things and shown how effective this is, people ask me a question, do you have a software that does this? And I have to shake my head and say, absolutely not. This is not a tool that we have or others have. It is a tool that you have to develop as an engineer. It is no different than playing a musical instrument. You got to pick up these conservation laws, put them together, apply to a control volume, reduce the math. It's a simple math. Even if you have nonlinear equations like this, there are very easy ways with the tools that we have in our software tool set to be able to linearize it and solve the problem. But this enables you to understand and comprehend what it is. So when you conduct an experiment, you know what you have to do. When you conduct a numerical simulation, you understand what are the important areas that you have to focus on and increase the accuracy or sensitivity in that area. Save your design and time. Analytical models presented here can be used by designers to quickly analyze the performance of a component. Based on analytical models, product design decisions can be made based on junction temperature and require airflow rate to manage them. rather than acoustic noise and others, in order to have all these other I think, I feel, or somebody else has done it such and such. Based on these models, expected life calculations and airflow requirements can be obtained in a short time interval. For the longest time in the electronics required to function for 15, 30 years, the life calculations were very, very huge. In the old times, we used to design for 30-year functionality. Nowadays, electronics operate for 5 to 7 years. Even at 5 to 7 years, that we have less robust components. As a result of it, we need to do the life calculation and see whether the system operates or not. And therefore, analytical modeling can be a pivotal vehicle for design process, enabling engineers to get a full view of the thermal and packaging requirements in a very short time interval. We're talking a small amount of time that's dedicated to be able to do this work for you, and you owe it to yourself and to your employers to be able to put these models together, do the analysis up front, and have an intelligent conversation with your system engineers, with your product managers, with your marketing folks to show why you have to go a certain path, why there's a cost increase as a result of what they're asking you. So the conversation is not going to be based on emotions and feeling, and I think it's going to be based on facts. You want to go with this thing, you have to put a $150 cooling solution in your system, and that's what's going to cost you. Can you afford that? Can we launch a product with that kind of a cost in your system? So with that, I thank you for your attention and participation. Remember, ATS has been in business for 25 years. We provide mechanical and thermal design services, cooling solutions, both air and liquid, instrumentation and wind tunnels, manufacturing services, and training programs, and our infamous QPD that we put out periodically. So with that, I thank you for your participation. And if there are any questions that I can answer, I'll be more than happy to answer.